Hello, everyone. Welcome to the first colloquium talk of the year. Um, just a quick announcement before we start. We are streaming this colloquium on YouTube so other people in the Columbia community can watch. And so just be aware that if you do ask a question during the talk, your face will also appear in part of that stream if you have your camera on. I'll turn that off for the question and answer section at the end, but at least the main talk portion will be publicly available. Okay, I think we can go ahead and get started. Dr. Priti Shah, we're so glad to have with us here today. She's a professor of psychology, education, and information at the University of Michigan and a faculty associate in the Research Center for Group Dynamics of the Institute for Social Research. She's published over 70 articles and chapters, is an associate editor at Memory and Cognition, and has received awards for teaching and mentoring at both the graduate and undergraduate level. Her work focuses on higher level cognition, things like thinking, reasoning, and problem solving, as well as the cognitive mechanisms supporting these abilities, and also how to apply these findings to educational settings. And so this research to me is really exciting because it's this rare combination of both basic science research into the limitations of cognitive processes, such as attention and executive function, and also the development of specific interventions for overcoming these limitations. So we're very glad to have us here with us today, and I'll turn the mic over to Dr. Shah for her presentation.
Well, thank you very much for inviting me. I've had the most delightful day meeting with people, and I am grateful that people are able to take the time out on a day that is otherwise important for other reasons. So thank you for being here, and got my inauguration pearls on. So I'm going to talk a little bit about our research in our lab on everyday scientific and statistical reasoning. And in particular, I'm going to focus on a few studies in which we are able to improve people's scientific reasoning skills. So what I mean by everyday scientific reasoning is the kind of reasoning that's required when you run into articles in the newspaper or on the internet, something like in the context of health, you might read something like 9 health benefits of asparagus, but you might also read asparagus amino acids help deadly breast cancer to spread, or eating asparagus may prevent a hangover. So all of these are different dependent variables. There are different consequences of eating asparagus. This is a health context. You might read how Facebook improves memory. Facebook makes us sadder and less satisfied. Facebook turns people into narcissists. So in the context of behavior, you might read a varied set of articles like that. Or in education context, you might read something like single sex education can plant the seeds of lifetime benefits for girls, or single sex education is unlikely to offer advantage over co-ed schools. So these are articles, and presumably your goal in reading these articles is to evaluate the evidence that you read about and perhaps make some decisions about your life based on these evidence. So normally when people learn science and scientific reasoning, they do so in the context of science classrooms, so chemistry, biology, physics. But here we're talking about contexts like health, behavior, education. And we assume to some extent that when we learn science and mathematics and we learn scientific reasoning skills like control of variables in the context of science class, that we're able to apply those to other scientific reasoning contexts like the ones that I just showed. And Bao et al. Tested this possibility, and he first started by asking people, how much do you think learning science and mathematics in school will play a role in developing students' reasoning ability? And this is a question he asked of pre-service teachers, and he found that, and then they were able to choose one of these options, 100%, 80%, 50%, or 20%. And pre-service teachers, both in the United States and China, reported that 50% or more of learning about scientific reasoning happens in the science and math classrooms. So people basically think that you can learn about reasoning through science and math. But then he also tested 5,000 students that were freshmen in science and engineering colleges in first semester physics with calculus in the United States and China. So they were both students at mid ranked universities in both countries. And they were given tests of in mechanics, electricity, and magnetism, and they were also given a test of scientific reasoning that comprised some slightly more domain specific things like conservation of matter and volume, but quite a bit of relatively domain general scientific reasoning skills like proportional reasoning, control of variables, probability reasoning, correlation reasoning, and so forth. And this is what he found, or they found that students in China did significantly better on the mechanics test than students in the United States. So these are histograms of the data and people's scores along the x axis. And China is red and the United States is blue here. Um, they also found on the test of electricity and magnetism that the students in China were better able to answer those questions accurately, and yet their scores in scientific reasoning were virtually identical. Students generally um, didn't differ, even if they were much better at mechanics and electricity and magnetism on the measure of scientific reasoning. So there are numerous reasons why everyday contexts are specific, are extra special, right? So one factor that we know a lot about from prior research is motivated reasoning. So people tend to want to accept what they want to believe and reject what you don't want to believe. If I love asparagus, I'm much more likely to reject the article that suggests that there might be a link to cancer. Um, our prior beliefs and expectations also play a role in evaluating this type of evidence. So we have a lot of prior beliefs about things like health, behavior, and education, like green vegetables are generally good for you. I might scrutinize data more if it's inconsistent with that prior knowledge that I have. And there's also, to some extent, trust or lack of trust in science. So some people say things like some of the reasons people give, I guess, for rejecting science, especially in the context of the kinds of headlines that I showed you, is scientists change their minds. You know, one day they tell you asparagus is good for you, the next day it's bad for you. Their predictions are often wrong. They say there's going to be 2 million COVID cases, and there's only been so many COVID cases. And scientists have agendas. So, and finally, there's no practice applying the kinds of reasoning rules that they may have thought about in the classroom, science, chemistry, or physics class, in the context of things like inclined planes and vehicles going down them or something like that, and in the context of everyday. So, in my lab's scientific reasoning work, we've been thinking a lot about, is there a set of consistent, somewhat domain general errors or heuristics that people use in evaluating science evidence? Who makes these errors? What conditions people are more likely to make, under what conditions are people more likely to make these errors? How can we people learn to avoid making these errors? And in particular, can we take advantage of motivated reasoning and belief bias? So if we can identify contexts where they might actually reject evidence, maybe we can use that as a lever to get them to think about the things that the more general reasoning principles that they could apply in other contexts. So before I go on here, I just wanted to tell you that I keep hiding the chat from myself. So if you want to ask me a question, you can ask on the chat, but feel free to just jump right in so that I might miss it. Um, so I'm going to talk a little bit about a couple of errors and interventions. And honestly, I'm just giving you a smorgasbord of stuff that I thought was cool, as opposed to a completely coherent presentation here. So I'm going to talk about some examples of threats to validity in scientific evidence and the extent to which people ignore these threats to validity. I'm going to give an example of statistical reasoning. I'm going to talk a little bit about information presentation and increasing trust in science and some conclusions. And like I said, this is kind of just a fun talk highlighting some findings and single experiments from different, more systematic series. So, there are various control experiments and follow ups and replications and such. And I'm happy to talk more about some of those. But I kind of just wanted to give you a taste of fun on a afternoon like today. So the first study I'm going to tell you about was conducted by Marie Burrich, whose picture you can see in the bottom right corner here, as part of her dissertation. And she tested college students on several vignettes describing science studies. And these vignettes contained one of four different types of methodological errors or reasoning errors about science. So, one was causality bias, which is essentially drawing a sort of unidirectional causal conclusion based on correlational data. Just want to clarify that sometimes that is an appropriate thing to do when there is a very well understood mechanism. But if there is not, or if there are multiple plausible causal models or mechanisms, then it's not necessarily appropriate to draw and recommend a causal intervention of some kind. So, um, another methodological error is poor operationalization of variables, not discussing how something was measured, or measuring it in a very gross or inappropriate way, or generalizing to a definition of a term, say creativity, when it was measured in one way, but you're implying that it's relevant in other contexts. Overinterpretation of small effect sizes. Again, this is a little bit in the eye of the beholder, because sometimes a small effect size really is quite important. So, just keeping that point in mind. And sampling bias. So they read these articles, and then they were simply asked to discuss whether the conclusions in the articles were valid. And then we also measured some prior belief and thinking dispositions. And in particular, the things that we asked people about were their need for cognition, like thinking is not my idea of fun. Um, we used a scale by Stanovich and West called actively open minded thinking. So no one can talk me out of something I know is right, is reverse coded item. A person should always consider new possibilities or change their mind when there's new evidence, are the kinds of questions that that scale asks. And then the cognitive reflection test, which is the ability to override prepotent incorrect responses in favor of current deliberate responses. Um, and as I said, causality bias is the tendency to erroneously interpret a correlation. So if A is associated with B, assuming that that means that there's a one-way causal relationship, that A causes B. Um, so here's an example of a study that contained this type of error that they were able to read about. As part of a recent study, researchers measured children's body fat and surveyed mothers about the amount of control they exert over their children's eating. The results of the study, conducted with 77 children aged 3 to 5, found that those with the most body fat had the most controlling mothers when it came to the amount of food eaten. This shows that when mothers exert more control over their children's eating, the children display less self control. So, this is basically advocating for a particular causal model when in fact there are other plausible causal models here. Um, Another example of article that they read is in the context of sampling bias. A recent study shows that Americans are more interested in politics than was previously thought. Researchers approached people at events such as town meetings and city council meetings, blah, blah, blah. You can see where that one is going. So when we had participants just discuss the study, and what we found was that in general, people were not very likely to make any particular kind of evaluative comment. So on the left set of bars, you see the percent of participants who simply provided some sort of evaluation of any kind, whether it was just something like they should have had more participants. And then on the right is the percent of participants, or the proportion of participants who explicitly referred to the flaw that was sort of highlighted in the article. So um, correlation causation was one of the higher ones. I mean, one of the lowest ones. Sorry, it's backwards. I study graph reading, so that's a little um, odd. Whereas people were more likely to notice the sampling bias errors that seemed pretty pronounced. So, what we also found was that college education seemed to play a role in people's ability and dispositions towards criticizing the studies that they read. So, seniors were much more likely to um, provide scientific levels, some kind of scientific or analytic evaluation of the data. Um, Seniors were also more likely to identify some flaws, and they were less likely to just talk about everyday experience as an explanation for the finding instead. Like, so what number of explanations means is something like, oh, yeah, my mom was always bossy about how much I ate, and that's why I'm overweight. So that would not be a scientific response to that. That would be an experiential explanation type of response. One of the reasons that she was interested in majors is that she was interested in some early work from, I think, the 1980s by Dick Nisbet that found that psychology majors were particularly good at certain kinds of scientific reasoning. So we wanted to see if psychology majors in the context of behavioral science studies were more likely to notice threats to scientific validity. But in fact, we found that was not the case. The people that were most critical of the scientific evidence were actually history majors in this case. And of course, this is correlational data, so we cannot draw a causal conclusion from this particular analysis, but it was slightly discouraging to us that psychologists didn't do better. Um, and then we found, replicating many, many, many studies over the years, that people were more likely to identify flaws when they were inconsistent with their prior beliefs than they were consistent with their prior beliefs. So this was kind of the first study in a long line of studies that we've done on scientific reasoning. And what we can conclude from this is that even intelligent college students rarely spontaneously identify flaws when the data are plausible. We find that when people are asked to be critical and to look for flaws in other studies, they are more likely to, but it's only just a little bit more likely to. We found that history majors are particularly good for whatever reason, and that prior beliefs infected people's evaluations. And finally, both actively open minded thinking and need for cognition correlated with the number of scientific evaluations and the number of flaws that people gave. So, the study I just presented, there was no correct answer. You were just told to discuss, and that's it. So that's a pretty low, in some ways, that's a pretty high bar, right? Like, you don't necessarily, when you're reading the internet, carefully evaluate the science of every article that you see. But what happens when we actually ask people to make head to head comparisons between two studies that are almost identical? Like, one was conducted at the University of X and the other was at the University of Y, and they had approximately the same number of participants and they did approximately the same things, but they had the same, one had a flaw and one didn't. Um, and how good are they in that case? So I think I will skim through this a little bit, but the flaws that it were included in some of the examples were things like attrition in one experimental group, such that there was no longer random assignment across two conditions in a study. Blocked assignment to groups. So the first 100 participants to arrive were asked to take notes by hand, and the second 100 participants were just assigned to take notes on a laptop. Self-selection into experimental groups, or a biased sample. So these are all different threats to scientific validity that participants were asked to identify, to search for. Um, so we had 150 around participants that were asked to judge 8 pairs of articles, and they were asked, out of the 2 articles, which of the articles use a method and data analysis that best supports the author's conclusions, and to what extent did participants included in the data analysis influence your judgment? And this is kind of what the articles look like. I find it's a lot of fun to create fake website type articles. So this is just an example of the handwriting class notes leads to a better memory article. And here's what we found. We found that even in the head to head comparisons, this bottom line here is 50% or chance, right? So you could pick one or the other by chance. People are on average slightly above chance for most of the article pairs, but not for one of the sample bias, which was a little bit more subtle than the other one. So, in general, people, even in the best case scenario, in this case, lay people online, were not particularly good at doing this task. But again, we found that actively open minded thinking was associated with how well people did. So, people with high actively open minded thinking skills were better at this task than people with low um, actively open-minded thinking skills. All right, so just to conclude real quick, even with head-to-head comparisons, people are only moderately above chance, and actively open-minded thinking again is associated with accuracy. All right, so this is where we get to the part that I really love, which is, can we increase attention to validity threats? And can we train people to do better? And so in this study, people read articles like the ones that I have showed you before. This particular one is about religious involvement and relationship between religion and marijuana use. Um, and I should highlight my collaborators, Audrey Michael and Colleen Seifert. And so we ask explicitly, should I start taking my kids to church to prevent them from using marijuana? So here we do. So, how can we reduce causality bias? And our hypothesis was that an instructional intervention that combines abstract rules with concrete examples will be helpful. Um, and that the abstract rule involved reasoning through, learning about the abstract rule through reasoning through multiple diagrams of causal models. So we had presented people with causal models, and they also had concrete worked examples about some contexts in which correlational reasoning is relevant. And then we took advantage of belief bias. So the examples in this case all involve plausible, easy to generate alternative explanations because they're less likely to believe the claims. Um, and so to teach them about modeling, we asked them to first specify what is the model that the author is claiming here. So in this case, it's A causes B, and they would literally draw out that model after being trained in causal diagramming. Then they were asked to think about a reverse model and a potential mechanism for a reverse model. Um, and then they were also asked to consider a possible third variable model. So maybe, C could cause A or B, and to come up with a potential third variable that might explain that relationship. And again, they had to draw it out. So essentially in this study, we had an intervention group and a control group. This particular one was in the lab. Um, so it was undergraduate participants. And at pretest, they got 3 scenarios and general diagram instruction. Then they got the instructional intervention and then a post-test. And the control group in this case didn't do anything in between the pretest and the post-test. And we had 3 measures of causality bias. The first one was, to what extent do the study findings support the journalist's conclusion that going to church deters marijuana use? So, in other words, can they see that the claims are not supported by the evidence? And that was on a scale from 1 through 5. We also asked evidence-based decision-making question. So after reading about this study, Michael decides to start taking his kids to church more often in order to prevent them from using marijuana. How likely is it that his plan will work? And then we were asked to have them ask them to generate alternative explanations. Now try to think of other possible causal models that could explain the relationship between church attendance and marijuana use. Diagram those alternative causal models below. So we use those at pre-test and post-test for the different scenarios that they were given. And I'm going to skip that because it's clear. Um, and so basically, the intervention was working through causal diagrams for two examples for which undergrads are able to come up with alternative explanations relatively easily as pre-tested. So one is the correlation between playing violent video games and violent behavior, which is actually one where you can get a 10-year-old to come up with the alternative explanation that video games may not cause violent behavior, but that violent kids might like violent video games and engage in violent behavior. Um, I think that's a very useful one for teaching kids about correlation causation. And then the second one was the correlation between taking Algebra 2 in high school and the later ability to land a top tier job. So, this is actually a true story. There was a correlational study produced, I think, almost 15, 20 years ago now, finding that people who had top tier jobs were more likely to have taken Algebra 2 in high school. And that led to 19 states passing laws, including Michigan, that you must take Algebra 2 to graduate from high school. That was one that was compelling to our Michigan students because they had all been, told that that was a requirement and why. So this is a little bit of more diagrammatic information about exactly what people saw. So this is the abstract intervention. So here's a causal diagram for B causing A. If that was true, then banning violent video games wouldn't reduce violence in schools. So we had them just reason through, and they also had to reason through in the empty circle. Please fill out one thing that could cause people to both take Algebra 2 as a high schooler and get a top tier job as an adult. And so here's what we found. These are Z-scores, and lower scores is better because lower means that you think that the evidence is not consistent with the claim. And so what we find here is blue is pre-test and red is post-test, that the intervention group is able to judge that the claims were not supported by the evidence. This is the claims evidence coordination question. Okay, good to go. This is evidence-based decision making. So asking people whether that that decision to say take someone to church more often is relevant. And again, you can see that the intervention group improved on that task. And then finally, this was the extent to which people were able to generate valid alternative models for transfer items. And again, the intervention group was better able to develop these transfer alternative diagrams. Okay, so this study found that causality bias can be reduced with a brief diagram intervention. And intervention improved the ability to generate alternative explanations for correlations, which transfer to novel contexts. And diagrams may scaffold abstract thinking about alternative causal models, and concrete examples may help people apply the rule better. So diagramming shows promise as an instructional tool. And also wanted to add that these results have been replicated in Intro to Research Methods undergraduate course and is currently being tested in adolescents. And we've developed through funding from IES, so a diagramming tool for adolescents that in which they read articles and then they go through our reasoning process using this web-based tool. And it is all part of a science in the news instructional set of lessons. So this particular set is about correlation causation that you can see here, but there's other interventions testing other threats to validity identification. I'm going to pause for one moment and take a sip of water and see if anyone wants to ask any questions. It's always so weird on Zoom. All right, so I'll keep going. People rarely notice threats to scientific validity, even when the result, especially when results seem plausible. And a combination of rules plus examples and diagrammatic reasoning might help. And next, I'm going to jump over to a whole different little topic of a different kind of error that people make. And so, yeah, I'm just going to do that. So we're going to start with a little joke. How old is this dinosaur? The museum visitor asks the docent. 200 million, 7 years, 4 months, and 2 days. How do you know so precisely how old they are? Easy. When I first started working here, they said it was 200 million years old, and I've been working here 7 years, 4 months, and 2 days. So following that joke, it turns out that this is not just a problem in the joke, but they're in real life. So this is from the previous Ebola crisis. And there was a woman who was a nurse who was working with Ebola patients, and she called the CDC before she got on an airplane, and she said she had a temperature of 99.5. And the physicians literally at the CDC said, I know you've been working with an Ebola patient, but your fever is only 99.5, and people with Ebola have fevers greater than 100.4. Go ahead and get on that flight. And meanwhile, in real life, she gets to her destination, her fever goes up, she actually does have Ebola. And this particular story, and more importantly, a story in which I had pneumonia, but the doctor didn't look at the chest x-ray because she just assumed I didn't, inspired me to study this particular statistical reasoning bias. And occurring both in the context of experimental studies, but also just individual data points. So are there stable individual differences in people's likelihood of taking numbers too seriously as too precise or more precise than intended across different contexts? To what extent can statistical reasoning skills account for number absolutism, and to what extent might number absolutism, what we're calling number absolutism, affect decision making? And finally, to what extent can we reduce number absolutism? And this work was done with Sinyu Pan. And this first study had 160 participants, and we had a survey of 12 items. A statistical reasoning questionnaire, standard questionnaire, and then a decision-making task. And so example of a comparison exam, John and Bob are taking the same math course. On the midterm exam, John scored an 88 and Bob scored a 90. How confident are you that Bob is better at math than John? Now, a decision-making item of something like this would be, John scored an 88 out of 100 and Bob scored a 90 out of 100. How much money, if you had $500 and you were John and Bob's parents, how much tutoring time would you buy for Bob and John? So if you were super absolutist, you might put all your money in the John tutoring. All right, so I'm going to skip these since they're just other context examples. And we find that I should have actually said something about referent absolutism. So referent is something like the temperature is 100.4. She's got the symptoms of strep throat, but only a temperature of 100.2. comparison is Bob versus John, so two different people as opposed to a referent. Both types of absolutism are related to poor statistical reasoning, but reference absolutism actually predicts decision-making performance above the standard measure of statistical reasoning. So the question that we had is that can we get people better at this particular context? And so participants did the same three things. They had the number absolutism questionnaire, including the decision-making items, the a numeracy scale, a standardized numeracy scale, and then training. And so there were two control conditions. One of them got training at the very end, one in the middle, and then the training condition got it at the very beginning of the study. And we use the same principles as our correlation causation intervention, which was abstract rules plus numerous examples. And so they had 8 different measurement scenarios, and subjects were asked to estimate the range of measurement error and list contributing factors to the measurement error in different contexts. So Lynn took an IQ test. She did better on one time than the second time. What would you estimate, what would you estimate the lower of the score might be if the average was 585, etc. And why might they perform differently on the two measures? And what we found, the bars here represent when they had the training. So the first control group, that's how well they did in standardized scores. So they did worse than the other groups. The people who got training at the beginning did better on both the number absolutism items and the numeracy items. But really interesting to us was that the control group that first did the absolutism items, then did the training, then did the standardized statistical reasoning measure, also improved on that. So we were pretty excited about finding those effects. And let's see here. I never know how fast or slow or detailed I'm going to go. So I have more than I need to talk about. So let's see. A little bit about impact of information presentation, because we have slightly new and different findings than stuff that has been done in the past on that topic. So to what extent does irrelevant neuroscience information, or I took out the anecdotal narratives, affect evaluations of data? And there's a lot of prior research in this domain. And most of the research in this domain focuses on evidence evaluation, like is this a good quality study? Or does the scientific reasoning in the article make sense, like the classic study by McCabe and Castell? But these two studies are just tests that assess whether people actually believe a claim. And the way in which we assess this is we first had them read an article. This one is about listening to music while studying helps you learn better. It's flawed in that people self-select to be in the music group or not. And then the beginning of the text differed. So it either discusses some mechanism that is, it discusses just some people prefer to work in silence, but some people listen to music, and shows a picture of a person with headphones, or they provide a possible implicit neural mechanism. So they say, listening to music engages cortical areas involved in music and sound perception, and this activation is thought to be present even when doing other tasks. But the key difference between this and other studies is that we asked them if the study would be replicated with an improved methodology. So if we did randomly assign participants, would you find that the study would be replicated? And we think that's a particularly interesting dependent variable, because it implies that you believe in the causal model, that listening to music causes people to do better. And so we actually find that if people do listen to music while studying already, they believe that the study can be replicated whether or not they had neuroscience. But if they don't listen to music while studying, so they didn't know very much about this, then they or didn't experience listening to music while studying, they were more likely to believe that the study would replicate if there was a neuroscience correlate. I'm going to pop into. We replicated this finding with a whole different context. How often you eat comfort foods when you're lonely and sad. And again, if you do, you kind of equally think whether there's neuroscience or not that it will be replicated. But if you don't, then the neuroscience really boosts the likelihood that you believe it'll be replicated. Um, and then we wanted to find out if this was a actual neuroscience effect or a lower level mechanism effect. And so in this next study, I'm going to whip right through. People read a bunch of different articles, like scenario would be tea reduces cold symptoms, and they were given either a macro level mechanism like tea decreases anxiety, which then affects your immune system and reduces cold symptoms, versus a micro level mechanism like tea decreases cortisol, which helps your immune system, which makes you have less cold symptoms. And we did this in the context of both human and animals. And I'm not going to talk about all these other variables here. Um, but but anyways, so in study one, we found that people prefer studies that include lower level mechanisms. That's not too surprising. But what I thought was especially cool was study two. And in study two, we asked people, this is a study in which there was a low sample size. We had they had only 5 participants per condition in this T study, and it was effective. But how many studies do you think, how many participants do you think you would need to be convinced that the data were true? And what you find is that when there is a micro level mechanism, people require fewer subjects before they believe the finding than if there is a macro level mechanism. So that suggests that it's the micro level of the mechanism that is playing a role in people's belief of data, whether it's neuroscience or a cortisol or something else. All right, and then I hid some slides about narratives because I wanted to give you one last little study because I'm greedy that way. The last thing that I've been interested in recently is people's trust in data. So there's a lot of research that finds that people find narratives or anecdotes more compelling than data. So if I hear a story about someone being cured of a disease by taking this medication, I'm more likely to opt for that treatment than if I see the data showing that it's effective, for example. So there's a lot of data of that kind. And one thing that I've been interested in is, why are data not compelling, and can we do something to make them more compelling? And so we did this particular study in the context of COVID, but we've also started doing it in a couple other contexts to see if it generalizes. Um, so like I said, there's a lot of evidence that people are influenced by narratives. And the typical proposed mechanisms about narratives is that they activate heuristics, they're experiential, they involve emotion, heuristic thinking rather than analytic thinking. But what if part of the problem is that data is actually untrustworthy to them? And so in this particular study, just before Thanksgiving, so hot off the press data, we asked 1,600 people about their Thanksgiving plans, and about a third of them said that they were planning on having Thanksgiving with dinner with people outside of their household. And in this study, participants were assigned to one of 4 conditions, and they were asked initially whether they were concerned about their family getting sick during Thanksgiving. And then they were given one of these 4 interventions. One is that they gave They were asked, what's the percent chance you would encounter someone who had COVID if you ate Thanksgiving dinner with 10 random people not in your household and there's a 4% infection rate in your community? So they actually see a graph that says if you did that, that would be about 40%. Um, we also gave them a narrative. Another condition was narrative, in which they read a story about someone who had been fairly COVID conscious but still got sick during a Thanksgiving dinner and regrets going to someone's house for Thanksgiving dinner. And then there was a data plus narrative condition. And I'm going to tell you about the fourth condition in a moment. So this is just the graph condition, your risk of running into a coronavirus positive person at a 10% person Thanksgiving dinner. They've already been told that it's in context that there's around 4% of the population currently test positive for COVID. And we find the typical narrative versus data story, which is that people who read the story are now more concerned about risk for their family after reading the story, but you get a backfire effect with the data. So with the data, people are less concerned about having dinner with others. And in fact, some of the participants made comments like it's unethical to scare people with fake inflated data, things like that. Um, and then, hold on. The data and story condition was approximately equivalent to the story condition. But what was really interesting was a brief, like 2-minute walkthrough of how we got to the 40% number. So they saw a icon array with 4 people out of 100 having COVID, and then they were divided up into different tables, Thanksgiving tables, and then they literally saw that there were 4 tables in this case of people that had COVID, and then they saw the graph. And what we find there is that data with an explanation for where that data came from did not backfire. So basically, and in fact was quite similar to what happened with the narrative. So that's just my last little example. So, in conclusion, everyday scientific reasoning is different from laboratory scientific reasoning. Thinking dispositions, and in particular, actively open minded thinking, the attempts to avoid being influenced by your prior beliefs and be willing to change your mind with new evidence. Um, we can identify specific reasoning biases, and there's sort of similarities across a particular threats to validity in scientific evidence that people either are able to identify or not across different contexts, although having prior beliefs or motivations to reject evidence makes them more likely to notice that specific bias. Across a couple contexts, we've been finding that abstract rules plus worked examples that are inconsistent with people's prior beliefs help people um, improve in their statistical and scientific reasoning skills. I think I just said that. Dispositions matter. And tentatively, that explanations increase trust in data and make data as effective as narratives. We have some new studies too on being able to interact with models to understand why they incorporate uncertainty but can still be valuable in science. And so finally, I just want to thank um, a lot of people here. So I had a whole lot of collaborators that I had pictures of earlier, but they're all listed here. The Basic and Applied Cognition Lab, the many scholars whose work, at least some of you who might be here, who have influenced this line of research, and you all for coming, and IES and NSF for funding a lot of this work. And thank you. I am more than happy to answer questions now. Maybe I'll just stop sharing too so I can see people.
Great. Thanks so much, Preeti. So yeah, anybody like to ask a question, you could either use the hand raise function and I can call on you to talk, or if you want to type in the chat, I can also read out questions. I can start with some of my questions. One thing that I found really interesting in when you were asking people about the chance that studies would replicate is that in general, the numbers, I guess they varied, right? But they got up, there were somewhere in like the 40 to 60% range or something right across the studies. And so um, I'm actually curious whether like, if we asked research scientists whether they would also be that. I guess I'm trying to figure out whether people that's pessimistic, that people are saying only half things are replicate, or maybe research scientists would actually think that's quite optimistic, that majority, that majority, a slim majority of studies would replicate.
That's a good question. And we haven't actually asked experts